Welcome to the Dolphins CST334 group project presentation video. The paper we have chosen to discuss for this project is Input and Output Coverage Needed in File System Testing. The presenting was done by Alexander, the scriptwriter was Reese, the slides were designed by Juan and Matthew, and the content review and video editor was Vivian. The reason we chose this paper for our group project is that we have been using the class-provided testing code for all our assignments, rather than manual testing, and we find the process of automated testing to be extremely helpful. If there was a way to have even more powerful testing system, that would benefit not just us, but all developers. Here we can see the make grade being run, which runs the grading script and shows results, and also shows the grade that we get on the assignment. And then next to that is the make unit test, which builds the unit test and runs the unit test executable one test at a time, and shows each test and what was correct or incorrect for each one. A part of this paper discusses the need for input and output testing to thoroughly evaluate the reliability, security, and stability of programs. The authors propose the use of the IO framework. This framework addresses some of the limitations of code coverage testing by focusing on testing outlier situations that are commonly overlooked by developers. The main topics that we will be covering during this presentation will be: what is the main problem being solved by the paper? Why is this problem important? What are the authors proposing? And how do the authors test their idea, and what do they find? The issue addressed by this paper is the inherent limitations of standard code coverage testing methods. Code coverage testing methods refer to the practice of testing all execution paths, but this doesn't verify that all edge case inputs will produce the expected outputs. These edge cases can vary based on the input type, and they can include boundary testing, empty inputs, special characters, invalid formats, out-of-range inputs, and resource limitation testing. Even when using high coverage testing, these special kinds of inputs and outputs often go untested, leading to missed edge case scenarios that can cause unexpected issues such as crashes, runtime errors, or even security vulnerabilities that malicious actors can exploit. Programs are used for almost everything in our lives, from life-saving machines in hospitals, to the integrated systems in our cars, to a clock alarm combination. These systems all have varying levels of importance, but regardless of the urgency, users will be distraught if their systems are easily exploited due to untested security vulnerabilities, if they crash due to uncommon cases not being properly handled, or if they display incorrect behavior due to out-of-range values. A person's watch going off at the wrong time might annoy the user, however, there are more dire situations. For example, if someone hits the brakes in their car faster than the program was expecting, and the traction control does not activate in a timely manner, the lives of the passengers and anyone else on the road near that vehicle are in very real and immediate danger. Even if we assume the system is not a life or death situation, if bugs are found in systems after it has already been deployed to the end user, making adjustments to their devices can be extremely challenging, especially if those devices are not internet connected. These post-deployment changes can also be quite costly to implement in some cases. The idea proposed in the paper is the implementation of input and output coverage in addition to coverage testing called IO coverage, or IO for short. This input and output coverage should test all edge cases, including things such as boundary values, corner cases, error path, and invalid inputs. Boundary values need to be tested in order to understand how programs will handle outlier situations. Just as an example, an integer in C++ has a maximum value of 2,147,483,647, and a minimum value of 2,147,483,648. And in the unique case where the maximum value is being held, what would happen if 1 was added? It's important to test these types of outlier situations because they can result in extremely unusual behaviors. For example, adding 1 to the maximum value in C++ will sometimes make the updated value equal the minimum value due to an overflow error. This kind of overflow error, when not tested, can cause all kinds of problems ranging from critical system failure to incorrect output. Testing by the authors. The authors conducted a real-world bug study on both crash monkey and XFS tests. The study revealed significant gaps in testing. To resolve the issue, the team created the IO code framework to test and validate the input and output of programs. These tests fill the gaps left by traditional testing methods by addressing and testing for under-tested scenarios, over-tested scenarios, edge cases, invalid inputs, empty inputs, and boundary conditions. The structured testing method can target potential issues more effectively than traditional testing methods. From a real-world bug study on ext4 and BTRFS, it was found that XFS tests cover the relevant code, yet still miss 53% of reported bugs, and in total, 81% of bugs were triggered only by specific syscall inputs or outputs. In conclusion, the paper shows that relying on code coverage alone misses many real file system bugs, since most issues hinge on specific syscall inputs or outputs. Their IO code tool fills this gap by tracking how well tests cover different arguments and return codes. They also introduce a simple deviation metric to highlight imbalances in testing. Overall, this work offers clear, practical steps for making file systems more reliable and paves the way for future testing improvements. A potential question to think about after reading this article is, what obstacles might limit IO code's effectiveness in large systems?